Hello. So recording started a little bit slow. So we did question 5. The notes will be on the OneNote. You can have a look. Question 6 is pretty much a repeat of question 5. So to get this, we have done separable functions. Dum, dum. And now we're reading this question. We're talking about the inner. We wanted to find the temperature of the outer surface area. So we want the temperature when R equals 0.2. But in order to find that, we first have to find C. So then we have to look at the information they gave us, which was all about the inner tube. So your radius is 0.14. They told us Q is constant down here. So this is a little bit of, it's all over the shop with the information. So you really have to go through and read it carefully. All right, we had the inner wall temperature as 400. And that the inner wall was obviously when the radius was 0.14. So we've popped all that in, and someone out there has found my C for me. What is it? Okay, 399.01. Good. When we've got this, we have got a lot of whole numbers here. So part of it could be, could you find an expression for C where you haven't rounded off and then put it back in? But that's a little bit of, I would be keeping this in my calculator as an answer value, right? And we might take this opportunity. Does everyone remember how to store things in their calculator? So if you have an answer that you want to use several times, right? So over and over again, doing that with you the other night, Josh, right? So let's say it's a hideous answer. I'm just going to use 5 for now because I'm not going to write in a hideous answer. You use your little arrow key here, and that's, but you're making it and you store it. So you go shift, and you can use, I said shift, I meant alpha. Alpha, and you can, I'm just going to go alpha A. So now every time I use A, it is going to be loaded as 5. So if I wanted to go 6 times 5, it's alpha A, and we get 30. So sometimes, most of the time, I think 99% of the time, it's just I'm using the previous answer, so I use my answer key. But if it's something that's I'm going to be using over and over again, I just store it there. And obviously, if you want another one, you can store it as B, C, and so on. So just something cute. So we've now got temperature, and you would put your, I'm going to put the minus Q in again. Q is constant, correct? Yes. Q is constant. We get 2, we get pi. I'm going to put K because the K changes on whereabouts in the pipe we're hitting, same as the radius. Okay, and our C, which you have hopefully stored in your calculator there as your answer. So now for part A, find the temperature of the outer surface area. So are we happy that that would now be the radius is 0.2? Now, at 0.2, this would be the inner part of your insulation. The insulation is touching, so that's why the K now has to change. So pretty wordy, lots of bits in there, but you should be used to that now with your stats questions from methods, correct? Hate those. So in we go. So temperature will be minus 60 over 2 times pi times 0.018 times ln 0.2 plus 399.01. What do we get? I stuffed. Sorry. It's the same K because it's still on the tube. I was getting a little bit excited with the insulation. That would be for part B. I apologise. So that should still be 19, and you get the 399. What did you say? 3. Whose idea was it to do this question? We want to find the outer radius of the insulation. So this time we're going the radius And I guess we're trying to find the outer radius. So we're trying to find R3. And this time the inner temperature here, that's what we've just worked out, correct? So that's going to be, we know that the temperature is going to be 399.8. Our C, is that still the same? And our K this time is 0.018. What else do we need? So we should have the temperature correct. We've got our K, that's a constant. We're trying to find this. That makes sense? So just a little bit different. And once you find your radius, Beth, which was, what did you say it was going to be? 0.387, so that means it's all the way there. Part C is then going, what's the thickness of the insulation? Well, you know what the radius 2 is. They told you. So hopefully the difference will be the thickness. But I liked the part B just because you were doing a little bit of rearranging using your probably just a little bit of ouch. So give it a crack. Request this one. So water evaporates from a lake at a rate proportional to the volume of water remaining. Suppose V is the total amount of water evaporated, T days, V naught is the volume of water. Explain why. Well, anyone want to field that one? Silence. The water remaining. So V is your original amount of water. V is the total amount evaporated after T days. V naught was the original. So wouldn't it be the rate at which the volume is evaporating? So this dV by dt is the rate that the volume is evaporating. It's going to be the difference between what you started with and how much has evaporated. Hello. A bit of a spiel or anything, but you're just saying that this is the difference in the volume, and you could start off by doing, like we've seen in a question before, that would be proportional to the difference in the volume. And then to get rid of that proportionality, it's times by a constant. Okay, so don't get caught up on this bad stuff there. We've got a nice equation. So we've got dV by dt equals K V naught minus V. So once again, we want to try and get an expression just to confirm that we're all happy. What are we trying to get by itself an expression for? V, right? I know we've got the V naught and the V, but because you're differentiating dV by dt, the V is the thing that we want. So how do we do that? How are we going to get it on the other side? Good. We must divide. You can't do an add or a take. You've got to do the division because it's got to be right up. Bang. So V naught take V by dV equals K by dt. Again, I'm being a bit naughty, leaving out that little step in the middle by dt, both sides, blah, blah, blah. Okay, you do the next line and integrate. Okay, so hopefully when you've integrated this, we know that that is going to be ln V naught minus V, but of course we've got the bracket. We've got the minus there, so we have to pop minus in the front. Okay, and that's going to be KT plus C. Let's get rid of that minus. We can chuck it on the other side. And so we've got ln V naught minus V. Now, you're more than happy to say take C if you really wanted to, but remember, it's just a constant. So I don't care if it's plus, minus, whatever. It's just keep it easier. It's just still a constant. And then to get rid of the ln, we're going to E the life out of it. So that means we get V naught minus V equals, and we've got E to all of that. But remember, when you're splitting it, E to the KT times E to the plus or minus C. So I'm going to short circuit and say that's A, E to the minus KT and in brackets, A equals plus or minus E to the C. Now, we've done that so many times that if you're still unsure as to why, just flag me down. Yes?
Why is there a negative on the left side? So negative element.
So we've got our little equation there, and now we have to, well, what is it that we're trying to find? Let's go back and read the question. 50% of the water evaporates in 20 days. Find the percentage of the original water remaining after 50 days without rain. Oof. So remember, we did a question like this earlier, that if we had something like 0.6 of the original weight, that's actually code for that 60% of the weight, correct? Because to find a percentage, we're timesing. You had to read the question. Was that 60% remaining, 60% decayed, whatever. All right, so let's look at what information we have. We've got 50% of the water evaporates in 20 days. So T equals 20. The volume is 0.5 of the original volume. Would we agree? And then we want to eventually find out what that is after 50 days. So after we've done some stuff, we want to slap in the 50 and away we go. The problem is that when we put T in here, we've got 20, we've got the V, we've actually got quite a few unknowns. Would you agree? So there's a little bit more information that's there that we haven't actually looked at. And it's all got to do with the original volume, maybe. And we're not going to find out that the original volume is 5 gigalitres or whatever, or 50 gigalitres. We want to find possibly maybe A in terms of, anyway, yes, Tom?
Well, when T is 0, volume is 100%. So.
Right, so when T of 0, go back up, volume is 100%, okay? So when T of 0, would we agree V equals V naught? So we're going to use this bit first. Okay, so what have we got? We've got V equals V naught equals, did it tell us what the original volume was at all? No. No. Minus A E to the, well, 0. So that becomes 1. Missed something. So go back, because that goes, didn't work. And then you go back and you reread the question. Suppose V is the total amount of water evaporated. And so from that, correct, we're saying at time equals 0, the amount of water evaporated is diddly squat. So, good-o. Oops. Oops. Okay, equals 0. So we've got, therefore, A, well, that makes more sense. A equals V naught. So now we've got V equals V naught minus V naught E to the minus KT. Agreed? Now we can use our next step. Using this, we can now pop that in. So V now becomes 0.5 V naught equals V naught minus V naught E to the, now there's 20k. Wowza. Okay, and what's going on here? We could have pulled out, back here we could have pulled out V naught as a constant. Agreed? Because as soon as you've done that, what happens? I can find K because the V naughts will cancel. So hopefully we're feeling good about this now because we've got our K value and now all we have to do is, what was it? How much, what percentage? Right, has after 50 days. So we're just going to sub in 50 and you're going to get, well, V equals something like a decimal times V naught. And that's when you are reminded about zoop. And I'll leave it for you. Read the question. Are we saying how much has evaporated? How much has disappeared? So you suss. And then read the next question. Okay, so we've got a lot of information over here. So that's the first thing I'm putting. We read for part A, we've got the temperature inside the fridge is at 5. So I'm probably putting TM equals 5. An object at 100 degrees is placed in the refrigerator to cool. So would we say, yep, would we say at T equals 0, the temperature is 500? 100? Why did I say 500? What goes on in my mind? I just don't know. After 1 minute, its temperature drops to, so temperature equals 80 degrees when T equals 1. How long will it take for the temperature drop to 10? So obviously that's going to be once we've found our C, any of our unknowns, in this case our K. We'll get to that in a minute, all right? So we're back to when in doubt, integrate the life out of it. So here we go. Similar, we've done one like this before. So T, take Tm by dt equals K little t ln T, take Tm equals Kt plus C. I hope we all agree with this. And we can use all of this information to help us find, so I mean I can even refine that and say that that is 5 plus a e to the kt, but we want to find, yeah, a would be handy, wouldn't it? So this is going to be great, okay? When we've got the a and we've also got this k up here, we should have seen by now, if we want to try and solve that easily, always look for when time is 0, because t times 0, you end up with nothing, and e to the 0 is 1. So what do we got? We've got 100 equals 5 plus a e to the 0. So therefore a must be 95, correct? So now we have temperature equals 5 plus 95 e to the kt. It's a bit of a pest because we still haven't found k, but lucky for us, we have got this information that we can sub in. We can then find k, and then, so sub, find k, and then you have your full equation. So then you can say how long it takes for the temperature to drop to. So then it will be find the t, little t temperature when, time when temperature equals 10. But find this first. Go, you good thing. Hello, we're just looking at people's work, whatever, and just a little note over here is that you have nice values. So when you find ln, if you can leave it as an exact answer, do so. Like sometimes you'll have decimals all over the shop and you go, oh, what's the difference? You've got rounding, you've got... But in this case, I think you do end up with, what was it is? No, what was the exact, mate? ln, you just, what was it, 75 over 95, what is it? Yes, what does that cancel to? 15 over 19. Shh. So whenever you're using trig or whenever you're using ln's and e's, if you round off too early, you can have a difference in your answers. So if you can keep it exact, go for it. At 6 a.m., the temperature of a corpse, was 13 degrees, and 3 hours later had fallen to 9 degrees. So a couple of ways you could do that. What did we have for this one? We had, when T equals 1. Sure. So we could say, if we're assuming this is so many hours after midnight, you could make that assumption. Then we could say that T6, and the corpse was 13. And then for this bit here, when it's 3 hours later, then it would have to be T is 9. Oh no, but it doesn't say what time it was. Hello, hopefully that makes sense. Wasn't recording, but that's for B. Just wanted to get you started so if we can at least finish this, and then, yes, please, even though some of you with the drafts, you're still working on that investigation to look at the formatting, just redo anything that I might not have found. So with this one, a little bit different. What's the first thing that might worry you when you look at this? I know what's worrying me. No, it's this. Right, you've got the I, and remember we said we want the I's to be, I guess for not such a mathematical technical word, pushed right up against the DI, like it's got to be multiplied there, and it's got that plus, so that's not too flash. So we're sort of, okay, we've got that in the back of our minds. They're saying these are the points. So it's not that they're changing, it's not that it's a rate. So the first thing we're going to do is actually sub these in. Okay, so please do that, write it down. Very quickly, as we said, this is not good at the moment because it has to be like pressed up in time. So one of the little things that you can do is put it back into forms that we've already played with. Even the board is saying enough. So we're going to get, you might be going, what are you doing? You're putting this over the other side. No good, no good. But basically what I want to do is now divide by this. So, and we've seen that before. Now I can do it as is. I'm looking at the 20 and the 10, so I can probably tidy that up, possibly, and say that that's 10, 2 minus I, agreed? And then I can say, well, now this is 0.3 over, and again, your call. You can say over 2 take I and leave the 10 there. You could put the 0.3 over there as well. DI by 10 dt, right? So Ash, if you wanted to, you can go, I don't like this, the decimal, so I'm going to get rid of that, times 0.3, divide, so you've got then 1 over 2 take I equals 30 dt, and you're integrating, it doesn't really matter. And then away you go. So the rest of it isn't too bad. It was mainly this step here, getting the I on that right side. So pop that in your repertoire. Hopefully you're not concerned with the t is approaching infinity. No? So you're looking at the graph or whatever equation you end up with, whack in a big value for t, like put 1,000, and it will tell you that's your limiting factor.